Hello, this is Mrs. Schroeder. We are back talking about chemistry. Today we're talking about molecular shapes. This is section 6.3 of your book. Our objectives are to predict the shape of a molecule using this weird term called VSEPR theory. We're also going to talk a little bit about polarity of molecules, not just bonds that we've learned about before. So shapes of molecules. We want to think about a molecule as a three-dimensional object. So far we've only been talking about Lewis structures, and that's really two-dimensional. We're writing it on a piece of paper. But in reality, we have 3 dimensions, and the molecule is going to use all of those. Because it does, it has different properties depending on how it's orientated in 3 dimensions. We do use a Lewis structure to help us predict what the molecular shape will be. We use it with this thing called VSEPR theory, VSEPR theory, which stands for valence shell electron pair repulsion theory. Basically, it helps us to find the shape of a molecule by figuring out the valence electrons around the central atom. We know that electrons will repel each other. They're all negative. They don't like to be near each other. They're going to try to be as far apart as possible. Like pushing 2 magnets together that are both the North Pole. They push each other apart. They don't want to be near each other. So shared electrons will be like that. Electron pairs are going to be like, they're going to try to repel each other as much as possible. Shared pairs that form different bonds will repel each other and remain as far apart as possible. So that's why they do this. In carbon dioxide, the Lewis structure for carbon dioxide shows that we have carbon with double bonds on either side. What this means, VSEPR theory, means that they're going to try to be as far apart as possible. They're not going to be orientated in space on the same side of the carbon atom. There's a repulsion here that makes them push this one as far away as it can until you get to this type of angle. Okay? They're as far apart as possible. Think about it on 2 opposite sides. As soon as this one tries to creep over this way, these electrons are going to repel it. So I have my atoms as far apart as they can. In boron trifluoride, I have 3 single bonds. This is a kind of odd one. This is one of mine that has a full octet even with only 6 electrons, and that's okay. Boron does that. It's small. So it has 3 single bonds, and you can see the best way to orientate it. When I do it on paper, it almost looks like I have a 90 degree, a 90 degree, and then another 180. In reality, they're all going to be as far apart as they can, equal distance away. So some basic shapes, make sure you write these down. A linear shape is 1. Trigonal planar, and we're going to talk about what those look like. Tetrahedral, and trigonal bipyramidal. So a linear shape is what it sounds like. It's a straight line. Trigonal planar means they're all in the same plane. Okay, so this one, if I had a sheet of paper and I held it flat, these bonds are all in the same plane around the sulfur. Okay, that's as close as you can see if you kind of look at this 3-dimensional shapes. Okay, tetrahedral arrangement means I have 4 of them, and they aren't 90 degrees apart like a square. They're actually in 3 dimensions. Will push each other even further apart to where you can actually kind of see in 3 dimensions. One's coming out at us, one's kind of going sideways, and the other one's kind of going up. But you have this 3-dimensional object where it's kind of in the different sides. The trigonal bipyramidal, it's almost like 2 planes sitting on top of each other, 2 pyramids on top of each other, which is why it's called bi in the pyramid. And we'll look at the video later. So again, shapes of molecules. We can look at if it has the examples I showed you already had all their bonds were shown with molecules or with atoms attached to them. In reality, lots of molecules have lone pairs. When I have a lone pair, I don't use it for the molecular shape. So shape is described only by the bonded atoms. Okay? So, for example, if I have hydrogen fluoride. So I have this atom. When I look at it, I see these electrons out here, these lone pairs. They aren't involved in my shape of linear shape. Okay? A bent shape would be something like oxygen and water with the lone pairs. These are in a tetrahedral arrangement, but I don't, if this is oxygen, there's hydrogen, hydrogen, and here's my lone pairs. So it looks like the tetrahedral from the other page, but I don't count my lone pairs when I look at the shape. The shape only shows you this part, okay, where the atoms are. The trigonal bipyramidal, same idea. This is our NH3. Is a common example of the trigonal bipyramidal. Now the difference between this, the trigonal planar, these were all on the same plane. In the bipyramidal, you can see that there's actually different planes. There's a lone pair rising up, and we'll show you with the shape things in class when you get here to have given a better idea. But the bipyramidal is not in the same plane, which is why it's going to look different than the trigonal planar molecule will. And the pyramidal has a lone pair. The planar did not. Now, each type of shape can be described by a bond angle. I can predict the bond angle based on what the shape is. So if I have something like this, arrangement is going to be this 180 degrees. Would be considered linear. Predicted bond angle is 180. It is in fact measured out to be 180 when we measure this bond. Okay. Trigonal planar, you would expect, just like a triangle split in three, you would expect to see an angle of 120, which again is what we see when we measure it out, 120. And the last one is the tetrahedral arrangement. And this is, you can see it's not a 90-degree arrangement anymore, so it's maybe the harder one to figure out. We actually find out that they're at 109.5 are the inside when we measure it out. So that's another kind of odd angle. You might want to make sure you write these down. Oops. Write down what these angles are, because you will need to know these common angles. And again, the shape of water, when I went through it, the Lewis structure shows the two unshared pairs. You find the shape with the four lone pairs, put them in, and you see the lone pairs are over here. You don't count them, so it just looks like this. Okay, a bent shape. Now molecules can be polar or nonpolar, and it depends on the bonds, but it also depends on what the geometry of that molecule is. So here's 3 rules I want you to write down. If the bond is nonpolar, the molecule will always be nonpolar. You can stop there. You figure out with your electronegativities, so you're going to use your electronegativities. And you know if it's greater than 0.5, greater than or equal to 0.5, it's going to be polar. If it's less than 0.5, it's nonpolar. Don't go on. Okay. If I find out that I have 2 equal dipoles meaning charges and they're in opposite directions, they'll cancel each other out and the molecule will then be nonpolar. So I can have a dipole with a nonpolar arrangement. And this picture right here shows you a dipole with a overall, the molecule overall is a nonpolar molecule, even though it has polar bonds. Okay, so this bond is polar, but the molecule is nonpolar because it's like playing tug of war. These 2 oxygen atoms are playing tug of war, and neither of them is winning. They're both equal, so it's a nonpolar molecule. I can have 2 dipoles though that are not canceling each other out. If they don't cancel each other out, then the molecule overall will be polar. And water is one that's a polar molecule. I have oxygen with hydrogen, and this bond is polar. But you can see they're not exactly equal. They're both pulling on it, but not on opposite sides. This one's not pulling opposite here. It's pulling in kind of the same direction. So overall, I do have a charge, okay, an overall molecular dipole. So I would call this a polar molecule. Alright, so we'll go through some more of these practice examples in class. Just make sure you have this written down, and we'll talk about it some more later.